Hello, my name is Ben Bucior. I'm a PhD candidate in chemical engineering, and today I would like to share a story on how we can make materials faster for applications like renewable fuels. But before we get into the specifics of my research, I'd first like to step back and zoom out to the larger picture of transportation. As a kid, one of my favorite things to do was asking my mom to drive around the neighborhood and help me find the dead ends. Yeah, it's true. Sometimes we would find interesting routes to get through the neighborhood or find new places. Even today, I really enjoy traveling. We can go to new places, see how people get around. Sometimes it's driving, sometimes by public transportation. And Chicago is a great place for this. On the picture on the right, this is by the Daily Center in the Loop. And here you can see several different modes of transportation if you look closely. There's a bus, people walking, people biking, driving, taxis. If you know the area, there's also subways under the street. However, with all of this transportation comes many costs. One that many people might be familiar with is congestion, traffic jams. The one I'm going to be talking about today, though, is pollution. Very specifically, greenhouse gas emissions. Greenhouse gases like carbon dioxide, CO2, have rapidly been increasing over the past several years. And out of these, 1 in 4 is from transportation. That means that this is a really big challenge because we can't tell people just to stop going places, but it also represents a huge opportunity because we can make a huge difference on climate change through working on this. So, how do we address this? The way I see it, there are 3 different ways. First, if you can avoid trips, that's going to be the most efficient trip you make. Second, can you find a different mode of transportation than driving? Maybe something like the train, or bus, or walking. Third, we can't completely eliminate these trips by car, and even trips by buses should be more efficient. So, can we find alternative fuels to reduce the greenhouse gas emissions? The train on the slide is an example in Germany where instead of using diesel power to power the train, they're using hydrogen. So, why hydrogen? One advantage of hydrogen is that whenever you put it in your car or train or whatever vehicle, the only thing coming directly out of the tailpipe is water. So, we still need a way to get hydrogen in the first place. Currently, this is predominantly through fossil fuels, but in the future, we can envision using electricity from renewable resources and allowing this to become a fully closed cycle. One reason, though, that hydrogen isn't pursued today is because of the amount of space it takes. Take, for example, a car that runs on gasoline now. If you put in, say, 10 gallons of gas, you might expect to get somewhere around 300 miles till you need to refill. And of course, your mileage may vary on that. So, if we did the same with hydrogen, at standard conditions, you would be expecting something like half of a semi-trailer of fuel. So you can't really tow that behind your car. Despite this limitation, there are some vehicles coming out of the market that don't look like the size of a semi. So these work by using high pressures, some 700 times the pressure of the atmosphere. That adds a lot of weight to the car, but also quite a bit to the cost. And so if we can find milder conditions, that would facilitate making hydrogen fuel more widespread. And so at this point, this is where my research comes in. If you picture a gas tank conventionally, it's basically just a big empty box. For the materials I work on, we would instead pack this box with this material, which has a very nicely defined structure with pores. And so what this does is acts sort of like a sponge that can suck in all of this hydrogen whenever you fill up the car, and then release it whenever you're ready to drive. To go a little bit deeper into this, they're called metal organic frameworks, frequently abbreviated as MOFs. So these assemble in what's called a building block approach, where you start with a metal, something like iron, nickel, aluminum, even things like silver or uranium, and then you combine them together with an organic linker. And here, organic refers to a branch of chemistry that means molecules that contain carbon. These act as a sort of plastic rod that link together these metals to these really nice three-dimensional framework structures. What's really cool about these materials is that you get not only the chemistry, but you also get very precise control of the shape. And so this, in principle, allows you to very precisely define what material you want for the application that you need. Because of this, MOFs have been explored for many different applications. One, in the topic of climate change, many of our current power plants still rely on fossil fuels. So what if we had a material that could capture the CO2 and store it or post-process it instead of just releasing it into the atmosphere? Second, a very tragic series of news articles keep coming out about stockpiles of chemical weapons. What if we had a material that could help us safely destroy these weapons into something that's a lot more benign and safe? And for the third one, this sounds a little bit more futuristic. So imagine for a moment that you're in a desert. It's really hot, you're parched, you just want something to drink. Well, what if you had a material that could capture the moisture from the air? Even the desert, even there, you have something like 20% humidity. And so researchers have developed a material that can extract even this little bit of moisture into a glass of water. With all of these, we can imagine even more applications. So the challenge really becomes is that we have very precise control of chemistry and shape. And we have a bunch of applications we would like to achieve with these materials. So how do we bridge this gap? The way I view the field, there are three main methods to accomplish that. The first is the way these materials have been designed throughout their entire history, the last 20 years. And that is that you think of an idea, you pick which metal, what organic linker, what shape you're interested in, and then you just go make it, and then you test it. And you learn more about how this material works. Maybe you find out that maybe you want something different. And so you go back and test it again. But this takes a lot of time, and you can only do a few at a time by this way. The second, which my group does, is we have ways to construct these materials on the computer. And these could represent both structures that have been made, as well as structures that we just hypothesize could be useful. From chemical theory, we also know how to describe hydrogen and other fuels. So, combining these, we can run simulations at the atomic scale and see precisely how these gases interact with the material. Then, depending on our application, say how much hydrogen can we fit in a tank? We can then count up the number of hydrogen atoms and run some calculations. The third area, which we're developing, is can we expand this even further? With simulations, we can access possibly thousands of MOFs, but can we expand this into millions? And so one way to do that is to collect all of these possible materials in databases. Possibly, there's been a material already made that the original researchers didn't think of for a different application. So can we reuse those? Can we search through here and find trends? Additionally, if you expand this to more and more materials, eventually even computer simulations are too slow. So can we design predictive models that can take the material and find more characteristics to describe the shape and the chemistry together that would allow us to decide how good of a material this would be for hydrogen storage or, again, whatever application. And so overall, the way I envision this is as a pipeline, where you have a material that you want, and you have a whole bunch of materials that you can choose from. To get from this point A to point B, we can use database methods and simulations to filter this down to, say, a handful of materials, which then becomes a lot more practical to physically make. But overall, what excites me the most about this research is that it's not just about hydrogen, and it's not even just about transportation. How I envision this is that going forward, we can develop this and expand this to be a more general method to design MOFs as a field as a whole, where we start with our materials that we can make, or ones that we hypothesize exist, and we have an application, and then we use this three-tiered approach with a combination of experiment, computer simulations, and data science together to make these materials a reality. Thank you.